Hello students, today we are going to study thermodynamics and some questions based on it. It will also involve kinetic theory of gases. So, let us go through some of the questions, and the first question is related to statement, and that is the explanation type of question. So, let us go through and see what our first question is. Yeah. So, it says the total translational kinetic energy of all the molecules of a given mass of an ideal gas is 1.5 times the product of its pressure and its volume. So, that is the statement, and another statement which is supposed to be an explanation is the molecule of a gas collide with each other and the velocities of the molecules change due to the collision. So, what do you think? Do you think the statement 1 is true and statement 2 is also true, and that statement true is the right explanation for the statement 1? And I want to know your answers. Do you happen to know that? Do you think that statement 1 and statement 2 both are true? And I think I can see the comments. Okay. So, let us discuss it in detail. So, as we know that for any molecule, the average kinetic energy of a molecule of a monoatomic gas so this being considered as average kinetic energy is equal to 3 by 2 kT. You might be aware that this part here 3 by 2 is the specific heat for constant volume of a monoatomic gas, and for this we know the total translational kinetic energy of all the molecules of a given mass is one. Is this part true? Product of its pressure means, is this thing equal to 3 by 2 PV? So, let us see if it is true or not. So, if the average kinetic energy of one molecule is this thing, simply total kinetic energy, total translational kinetic energy that we are talking about is equal to how many molecules do we have? Number of moles times the Avogadro number, n. So, if we multiply Avogadro number capital N with this quantity, we get R, right, Rydberg constant. So, 3 by 2 R T, T being the absolute temperature, and times N, smaller n, that is the number of molecules. So, let us say I am writing it like this. Now, by gas law, we know that PV, pressure times volume, is equal to nRT. It gives us 3 by 2 PV. So, yes, our statement 1 is right. Now, statement 2, the molecules of a gas collide with each other. Yes, they do, and the velocity of the molecules change due to that collision, that is also true. But do you think this explains this? Means even if it is true and it is somehow affecting this, it cannot give us any formula, any data regarding how it comes out to be 1.5 times product of pressure and volume, or how it is related to the concept of CV, which is 3 by 2 K. So, of course, this cannot explain this. However, both are true. So, we can say that statement 1 is true, statement 2 is true, statement true is not a correct explanation for statement 1. So, our correct answer is B. Now, let us move on to our next question, which is again a numerical, and in this time we are going to find some energy, decrease or increase in internal energy. Let us see what we have. 1 mole of a monoatomic ideal gas undergoes an adiabatic expansion. So, what do we know about adiabatic expansion? We will come to that, in which its volume becomes 8 times its initial value. If the initial temperature of the gas is 100 Kelvin, then the universal gas constant R equals to 8.0, which is a approximation, joule per mole per Kelvin. The decrease in its internal energy in joule is. So, first thing we must note that what is the amount of gas we are talking about. So, it is 1 mole of a monoatomic ideal gas. Monoatomic ideal gas, what does that tell us? That tells us that CV has a value 3 by 2 R or K for a single molecule, but for 1 mole it is R. CP, what is CP? CP is the specific heat capacity of a gas when pressure is constant, is equal to 5 by 2 R, and this also is related to a quantity gamma, which is called specific heat ratio, is equal to 5 by 3 for monoatomic ideal gas. What else do we have in our question? Our question says that it is going through an adiabatic expansion. So, it is an adiabatic expansion. So, the graph would look like something like this. I would not say it is symmetrical towards symmetrical about its axis, but somehow it is a curve along PV graph. Let us say this is pressure and this is volume axis, then it has a curve something like this, and it is an expansion. So, are we going from here to here or along the downwards towards the curve? Obviously, it is expansion, that means volume is increasing. So, obviously, it would go along this way, therefore, down the curve. So, let us work it out in a proper numerical way. So, let us start. This is our pressure, this is our volume axis, and this is the curve we are talking about. It says that the volume has expanded to 8 times of its initial value. So, let us say we started with volume V naught, and our final volume is 8 times this, that means 8 V naught. Obviously, the initial temperature given here is 100 Kelvin. We are just marking it here. First, we need to find out T2. We know T1 equals to 100 Kelvin. So, what is T2? To find this, we can use a relationship between temperature and volume for adiabatic. We know that PV, when we are talking about adiabatic process, we know that this relation holds true. PV to the power gamma, where gamma is the specific heat ratio for a monoatomic gas, is equal to constant. So, but we do not have any information about pressure. We have information about temperature. So, we will not use this relationship, but some other relationship obviously derived from this one. That one is temperature times volume to the power gamma minus 1. Please note that this whole quantity gamma minus 1 is in exponent, and the base is volume, and this is over the volume only, not over temperature. This equals to constant. Now, if such relationship holds true, that means temperature, this thing here, the whole quantity here and here are equal. So, let us say we say T1 V1 to the power gamma minus 1 equals to T2 V2 to the power gamma minus 1. Now, we know what is the value of V, means we do not know the value of V, but we know that how much it has expanded. So, let us take T2 in terms of T1 and V1 V2. So, what is the value of T2? If we take this whole expression, this part here towards this into the denominator here, we are getting T2 equals to T1 times V1 to the power gamma minus 1 divided by V2 to the power gamma minus 1. We can write this as V1 divided by V2 the whole to the power gamma minus 1. Now, can we solve for T2 now? Let us see. We know V1 is V naught. Let us write it V naught. What is V2? 8 V naught. What is gamma? Did we discuss something about gamma in our previous slide? Gamma equals to 5/3 for a monoatomic gas. We can put this value here, 5/3 minus 1, that is 2/3. So, let us erase this part and write our new expression as 2/3 here, power 2/3. Now, we can cross this out, right? V naught, V naught. That means 1 by 8 the whole to the power 2/3, that gives us 1/4. So, our answer here means not answer, but the temperature that we are finding currently. Final temperature T2 is T1 divided by 4. And what is the value of T1? 100 Kelvin. That means this temperature is 25 Kelvin. So, it should be capital K as the symbol of Kelvin. Okay. Now, we have got the value of T2. Can we work out the work done by this monatomic gas? Means obviously it is an expansion, the work done by the gas, not on the gas, by the gas is positive. So, what we are looking for? We are looking for the work done by the gas, and that would be, yeah, let's. So, for an adiabatic pressure, we know that delta U equals to 0 and the work done is equal to the change in heat, means the heat supplied to the gas, means the work done by the gas is equal to the heat supplied to the gas. That is why there is no change in the total internal energy. So, that we can work it out. Total internal energy, change in internal energy would be number of moles into CV. What is CV? CV is the specific heat capacity of the gas when volume is constant times delta T. And we know that this comes out as, we have 1 mole, right, 1 mole. So, value of N is 1, CV equals to 3 by 2 R times delta T. Delta T is 100 Kelvin minus 25 Kelvin, that we worked out is 75 Kelvin. Now, if we work it out, we already know that value of R we are taking is this. So, if we just put the value here, 3 by 2 times 8 times 75, we are getting 75 times 4, 300, 300 times 3, 900, 900 joule. I hope this much is clear. Everything in this equation in question in this numerical has gone linearly, so I do not think there is any scope of confusion, but if there is any, please let me know. Okay. We are moving to our next question, which is again with thermodynamics, and it also deals with monatomic ideal gas, and it has something of matching type. So, it says 1 mole of a monoatomic ideal gas undergoes 4 thermodynamic processes as shown schematically in the PV diagram below. So, this diagram shows 4 processes. So, let us count it together. This one is process 1. This seems like an adiabatic process because this is not exactly symmetrical, but let us see if it is not. Let us talk afterwards. 1, 2, pressure is constant, that means this is an isobaric process. 3, volume is constant, isochoric process, and 4, 4 let us consider it is going from 3 V naught to V naught and P naught to 3 P naught, means if we consider the product of pressure and volume, that would be 3 P naught V naught for both these points. That means this is an isothermal process. The product of pressure and volume are is constant. That means temperature is constant. PV equals to nRT. PV is constant, therefore temperature equals to constant. Now let us see what we have to match. So on the list 1 it says in process 1, process 2, process 3 and process 4. List 2, let us read it. List 2 first thing says work done by the gas is 0. So work done by the gas is 0 when there is no change in volume, right? And that is happening when volume is constant and pressure is dropping from 3 P naught to P naught here, this part 3. Pressure drop is there but volume has no change. That means the work done for this process is 0. That means that is process 3. We can relate like this. Second thing is temperature of gas remains unchanged. Temperature of the gas remains unchanged. That means we are talking about an isothermal process where temperature is constant, and we already discussed that's 4, process 4. So here we have process 4. Now third, no heat is exchanged between the gas. So we know that all the 3 processes here 4, 2 and 3, we can see that heat would be exchanged because this is an isochoric process, this is an isobaric process, this is an isothermal process. Only one part here, this first one seems to be something different, and we know that an adiabatic process has a slope. In a PV diagram, the slope is slightly greater than that of isothermal process, and we would get this might be something of adiabatic type. So yes, no heat is exchanged between the gas means adiabatic process is process 1. Now let us see fourth, work done by the gas is 6 P naught V naught. Work done by the gas is 6 P naught V naught. Work done for this process, we cannot say, we can say this is 0. Work done for this part, we cannot say, we do not know what is the value of volume here. For this part we can say, but obviously it will involve some logarithmic value, and that will, if we are finding our expression work done in this format, it would involve some log of something and it would be not so easy. Let us see process 2. So this is an isobaric process, and we can simply say that work done would be P del V. What is the value of P here? 3 P naught, and del V means change in volume. 3 V naught minus V naught, that is 2 V naught. 3 P naught times 2 V naught, we are getting 6 P naught V naught. And yes, so our fourth point is process 2. So let us see which one is our correct answer. P is 3, Q is 4. No, this is not. P is 3, Q is 4. No, this is right. R is 1 and S is 2. Yes, this one is right. I hope this is making sense. We are moving to our next question. Okay. So what does our next question ask us to do? 1 mole of a monoatomic gas, again monoatomic ideal gas, undergoes a cyclic process as shown is in the figure. So, one thing you should really consider, this is temperature versus volume. So, do not consider it a PV diagram. What one mistake could be done here very easily, आप ये समझ सकते हैं कि ये PV diagram है, this is an isobaric process, this is an isobaric process, this is an isothermal process, this is an adiabatic process, but this is not so. We have temperature versus volume. So, if we say this is constant, temperature is constant, we have isothermal process, again isothermal process, no isochoric process. We can say those could be something like isobaric, but we do not know yet until we explore that. So, let us discuss it. So, which of the statements below is true? So, first statement is process 1 is an isochoric process. Does it look like an isochoric process? Volume is from this value to this value, it is decreasing. So, obviously, it is not the right. This is not true. Let us see P. In process 2, gas absorbs heat. This is an expansion. Volume is constant. Sorry, volume is increasing, temperature is constant. So, yes, this is an isothermal. Isothermal expansion. Sorry for the wrong spelling. Yeah. Isothermal expansion. Would this be absorbing heat? Means gas is absorbing heat. That means gas must be doing some work. Yes, gas is doing some work because volume is increasing and the temperature is constant. That means internal energy is directly proportional to temperature. If temperature is constant, there is no change in internal energy. That means work done by the gas is equal to the amount of work done by the gas is equal to heat supplied to the gas. So, if there is work being done by the gas, there must be some heat supplied to the gas. Therefore, gas absorbs heat, and yes, that is right. In process 4, gas releases heat. Process 4, what is happening? Again, it is, no, this is not an expansion, this is a compression. Volume is decreasing, temperature is constant. So, yes, gas is releasing heat. Means there is some work done on the gas. Gas is acquiring energy by the work done on it. Therefore, it must release some heat to maintain that constant temperature. Yes, gas releases heat. Processes 1 and 3 are not isobaric. Let us see. Okay. So, in terms of temperature and volume, isobaric means pressure is constant. For pressure is constant, we can say if pressure is constant, that would be PV equals to nRT. So, that means V is directly proportional to T. In that case, our graph should be something like this sort, of this sort or this sort. Means what is happening here? Volume is directly proportional to temperature. Therefore, the graph of volume and temperature for constant pressure would be linear and would be passing through the, what do you call it, origin, that is T equals to 0, V equals to 0 point. But none of these graphs are something like that. So processes 1 and 3 are not isobaric. So this is true. So our answer is B, C and D are true. Okay. Let's see what we have next. Yeah, this is an interesting question that I made with. So let's read it. 1 mole of an ideal gas is taken from A to B. So point A, this is a PV diagram. Be assured that we are not getting confused with TV diagram here. This is pressure versus volume, and two processes are going through. Means one process is the solid line here and another is shown in the dotted line. If the work done along the solid path is Ws and along the dotted line is Wd, then the integer closest to the ratio Wd by Ws is. So first thing you can see that if you find out the volume, the work done in this PV diagram, any PV curve gives the work done by measuring the area under the curve. So if you measure the area under the curve, you can simply find out the work done. So which one is easy? Obviously this is giving us a very straight answers because we have a rectangular pattern, we can obviously calculate easily. So let's calculate the work done in this part for the dotted process. So work done in this process is from 0 to 0.5 to 2. The change in volume is 1.5, right? 1.5 liter times 4 atmospheric pressure. I am just considering the volume in terms of liter atmosphere, work done in terms of liter atmosphere. So work done here is 6 liter atmosphere. For this part we have 1 atmospheric pressure and change in volume is 2 to 3, that is 1. Again 1 times 1 is 1 liter atmosphere. For this part we are getting something off the short. I think this is 3.0.5.5. So change in volume is 2.5, and if I consider this, this part is not getting clear. Okay, this might be something of by calculating these dots. So you see, if we consider the solid line, we are getting the P times V, pressure times volume, as 0.5 times 4, 2, here 1 times 2, 2, 2 times 0.5, 2 times 1, 2, again 4 times 0.5, that's 2. That means this is this is an isothermal process where P times V is constant. So that gives us 3 times something that is same as 0.5 times 4. So 3 times something should be 2, and that is 2 by 3. That means the work done for this process is 2 by 3 times 2.5, that is 5 by 3. Again in the same unit, liter atmosphere. Now what is this? This is a PV curve for a isothermal process because P times V is constant, and that is what we had to use here. Okay, I think some part is here is hidden because of the diagram. Let me complete it. Then the integer closest to WD by WS is, so the integer closest to WD by WS, we already found out the total volume of value of WD as 6 plus 1 plus 5 by 3, that is 7 plus 5 by 3 means 8 plus 2 by 3, or 23 by 26 by 3 liter atmosphere of work. Now if we calculate the work done by the solid line, we have a common, means we have a formula for this, for isothermal process. We can use our formula and work that out. The work done in this isothermal process is equal to yeah, we know 2.303, or simply if we don't use that, 2.303 is equal to PV times ln V2 by V1, or we can say PV times ln P1 by P2. Both these expressions are same because V2 by V1 equals to P2 by P1 by P2 when temperature is constant, and again PV, we can write this thing as nRT as well, but here we know the value of PV. PV is constant, as that is 4 liter atmosphere times ln P2 P1 by P2. So P1, let's not consider this, consider V2 and V1. V2 is 5.5 and V1 is 0.5. So 5.5 divided by 0.5 ln of this, we are getting 4 times ln 1.1, not 1.1, ln 11. Ln 11, and we can solve this as 4 times 2.303, which you know log log and ln are related functions, and they can be related by ln of something is equal to 2.303, which is the value of ln of 10 times log of that value. So, log x is equal to 2.303 times, sorry, ln of x is equal to 2.303 times log of x. So, ln of 11 is equal to 2.303 times ln of, again I said ln, log of 11. Log of 11 is very close to 1, it would be something 1.02 or something. So, if we solve it out, it give us the value around 4.8. Means in my previous calculation I had calculated it to be 4.7966 something. So, the closest calculation in 1 decimal point is 4.8. Now, recall what we had calculated about Ws. Ws was 26 by 3. So, what we had to find out, Wd by Ws, right? So, Wd by Ws is equal to 4.8 divided by 26 by 3 is equal to, we take this thing up, Ws is 4.8, Wd is around 26 by 3, which is around 8 point something. So, yeah, we are getting around 1 by 2. So, if we had something like Ws by Wd, yeah, Wd by Ws, it would be, sorry about this confusion in the calculation, let me work it out. 4.8 divided by 8.23. Okay, I have been working out Wd here, which should not be here, it is Ws. Wd has already been calculated as 26 by 3. So, 26 by 3 divided by around 4.8, which we would be getting 8 point something divided by 4.8, we are getting around 1.7 something, and which is closest to the integer 2. So, our answer is, the integer closest to this ratio is 2, and that is our answer. And I am very sorry that I took a long time in calculating that, but if you have any doubt, please let me know through your comments. And we have another question which is again related to thermodynamics. Let us see what we have. The figure shows, this is a figure again a PV, pressure volume diagram, and it shows us a complete cycle A, B, C, D, A. So, the figure shows PV plot of an ideal gas taken through a cycle A, B, C, D, A. The part A, B, C is a semicircle and CDA is half of an eclipse. Then first the you have to find out which of these statements are true. So, statement 1, statement A says the process through the path A to B is isothermal. Is it true? Isothermal. So, for isothermal, let us consider point A and point B. At point A, the pressure is 3, the volume is 2. 3 times 2 is 6. For point B, the pressure is 2 and volume is 3, again 6. So, can we say PV is constant? Let us see the middle points. Let us consider this. This does not look like it is constant. If we had something like this, we could say that this is an isothermal process, but not this. So, yes, this one is not true. The process during the path A to B is not isothermal. The heat flows out of the gas during the path B to C to D. So, let us consider that B to C to D. We are considering this part. Heat flows out of the gas. That means heat is flowing out. That means delta Q is negative. So, is it true? Let us see. P to V, is it a volume is decreasing or increasing? No, sorry, B to D, volume is decreasing obviously. Let us see the product of P and V is decreasing or not. Product of P and V, 3 times 2, PV is 6 here, 2 times 1, that is 2. So, here it was 6, here it was 2 times 1, 2, here it is 1 times something smaller than 1.5, let us say it is 1.3. Now, it is 2, but it is quite close to 0.5. So, let us, this part is 1. So, the value PV is decreasing 1, 6, 2, 1.5, 1.3 and 1. So, PV is decreasing, that means the temperature is decreasing, because PV is directly proportional to PV is equal to nRT, that is directly proportional to temperature. So, if PV is decreasing, temperature is decreasing. So, that means delta U is negative. So, if delta U is negative, delta Q is negative, then what can we say about the work done on or by the gas or system? So, we know that if or no if, simply delta U means change in the internal energy of the gas is equal to delta Q, that is heat supplied to the system or the gas, plus the work done on the gas, or we can simply say delta Q minus work done by the gas. So, you can see that from B to D, the volume is decreasing, and if the volume is decreasing, work is done by the system. So this part is positive. So, and we know that this is negative and this is negative. So, we know that this part is negative, and we know some negative value plus delta Q plus something positive. That means this thing has a more negative value than delta U, means it is sure that the heat supplied to the gas is negative. So heat flows out of the gas is right, means if heat flowing out of the gas, that means supplied heat is negative. So this is true. Now let's see what is point C. It says work done during the path A to B to C is 0. So A to B, work done here to here, and then B to C. So let's erase these parts first and now discuss this. A to B and then B to C. So we are considering the whole part here. So why don't we break it into A to B and then B to C. For B to C, we can say that this is the whole work done. This is a compression, volume is decreasing, therefore work is done on the system. Now consider this whole part, A, B and the rectangular structure below. This is the work done by the system, by the gas, because volume is expanding there. So obviously this thing is smaller by this thing, and this is the difference. This semicircular region is the difference. So we can see that for whole this process from A to C, the work done by the gas is equal to the area of this semicircle. So we know that the work done by the gas is positive, and but this statement is saying that work done during path A to B to C is 0, which is not true. This is wrong. We just came out that A is also wrong, B is right. Let's consider D. Positive work is done by the gas in the circle A, B, C, D, A. Okay, the same concept here. For the whole means we discussed A to B to C on terms of how do we find the work done by measuring the area below the curve. Here also we know that for this part here, D to B, for D to B, the work done is equal to this whole thing, and here work is done by the system because volume is expanding. For this part B to D, work done on the system because volume is shrinking. Now which is greater, work done on the system or work done by the system? Work done by the system is upper curve, work done on the system is lower curve, means this part, this whole area is the net work done by the system, by the gas. So positive work done is by the gas in the cycle ABCD. And yes, this is right. Our answer is B and D are the right choices. So that concludes our session. We'll meet again with some other subject. Be ready and be prepared for our next session. Thank you.